Well, welcome back to LeetCode 105 question. So let's study what it tells in the question. Construct binary tree from preorder and inorder traversal. That means इस question में हमें एक binary tree construct करना पड़ेगा from the inorder and preorder traversal. That means tree का जो भी inorder and preorder array structure, array traversal order होता है, that's already given in the question. Inorder, this is preorder and this is inorder. And we have to return the binary tree also in the array form. This is the output. So we have to return like this. So this comes under a medium level question and it's really very complicated. So first let's start understanding. So to solve this question, what we have to do in the first part, we have to just pass the binary from the main function. So we have already done that. This is solution. We have created an object here. This is the object and these are the arrays preorder and inorder, and from here we have passed this one. So okay, now we'll be constructing the main theory, and before that let's understand that how we can solve it. Okay, so first let's understand the concept that here we have to return, हमें यहाँ पर actually binary tree construct करना पड़ेगा from the preorder and inorder. So what is the order of preorder? This is the tree 3, 9, 10, 5 and 7. So the preorder is this preorder of the tree is 3, 9, 20, 15, 7. This is the preorder, and the post order and this inorder. The inorder is this in order, that is 9, 3, 15, 27. So this is the inorder. So we all know that preorder. In preorder, first there is the root. That means preorder में root हमेशा front में होता है. So in the preorder, the root is always in the front. So first there will be root, then there will be the left part, and then there will be the right part. This is preorder. And in order, the root is always after the left. So in order is like this: left, root, and right. And from this the combination of those two arrays, those two traversal, that is from preorder and inorder, we have to construct the binary tree. So how we can construct it? कोई भी binary tree construct करने के लिए we have to first detect the root. हमें root को निकालना पड़ेगा. So if you just observe the preorder, the first in preorder, the first is always the root. So this first is the root here. That means this 3 is the root. Okay, we got the root from here. मतलब हमने preorder से root को निकाल लिया. Now one thing, if you notice in this inorder series, the root is in the middle. That means the root will be in the middle portion, and in the left side, root की left में जो भी होगा that will be of left tree, and root की right में जो भी होगा these will be a part of the right tree, like this: left tree and the right tree. So that is the construction of left and right. So as we have gotten preorder from, we can detect that this is the root. So we can get from here that is the root. मतलब we can get the preorder root from here, and then we can construct the inorder root from here. Once we get the inorder from here, now we can easily understand that whatever the elements in its left side, इसके left में जो भी elements है, these are the part of left tree, और इसकी right में जो भी elements है in the right side, these are the part of right tree, right subtree. So this is what we have to do, and this mechanism we have to apply a recursion for it, that it automatically detects again, and it works. So how we can start? So first we have to initialize the method, and after that method we have to start working with this one. So this is the beginning. So first we have to notice the constraint. Few constraints were given, so we can start from there. Let's study the constraints. Okay, now notice there are a few constraints told that 1 less than equals to preorder dot length less than equals to 3000. That means here the first constraint is that the preorder, मतलब जो भी preorder या फिर inorder है, that is not null, that has a length between 1 to 1000. So the first constraint we get, first constraint preorder, the length of that means preorder is not null. The first constraint we get from here, that is preorder is not null. Preorder or inorder, whatever is provided, that is not null. This is not equals to null. The first constraint. Second constraint, what it tells, that the length length of inorder.length equals to preorder.length. I mean, that means the length are same. The length of both the preorder and inorder, that means preorder.length, must be equals to inorder.length. This is the second constraint. Now we'll be noticing the third constraint. So that is within 3000. Preorder in order consists of unique values. Each value of in order also appears in preorder. Preorder is guaranteed to be the preorder traversal. So these are guaranteed to be the preorder traversal. So one thing we can notice from here, that means if preorder, if in any case preorder becomes null or their length, if this length becomes not null, so we'll be ending our loop, we'll be returning there. That means that is the base case. If we get not null condition, that means that is violating the constraints, so we'll be ending our program here. Preorder and inorder must not be null. If it becomes null, somehow, so we'll be stopping our program here. So this is the base case. So let's write the base case. Okay, preorder in order, that is, so that is the base case. So let's write this base case. Okay, so let's start writing. So first we'll be checking if preorder equals to null, that means it is one of the stopping or terminating case. Or in order equals to null, or the length is not equal, that is preorder dot length not equals to in order dot length. If the length is not equal, then simply we'll be returning null. That means we'll be stopping working the program. Next we'll be utilizing a helper function to initiate the program. So let's make the program. Let's call this build tree helper function. So we'll be calling this return build tree helper, and here we'll be passing the arrays. Preorder, we pass the array, this is preorder, then we passed it in order, then we'll be passing the starting index of the preorder, so we can call it a pre-start also. So now we'll be passing the value of pre-start. So the initial value of pre-start is always 0, so we are passing this pre-start or 0, because the initial value of pre-start is 0, so we'll be passing, let's call it integer pre-start. So we'll be passing integer pre-start, and then we'll be passing integer in start and integer in end. So integer pre-start, that is equals to 0, initially that is 0. Integer in start, that is start of in order, that is equals to 0, and then we'll be passing the integer in end, and this will be in order dot length minus 1. Okay, so did you got it? That now we're creating the pre-start, in start and in end. So we'll be passing all the pre-start, in start, in end to the function. So now passing this pre-start, in start, in end. So we are passing those values from here. Now we have to construct this function. So let's construct this function. So this is a function that will be actually returning us a root. So our return type must be of tree node. So private, now the return type will be tree node, private tree node, and then build tree helper, and then we'll be expecting all the arrays. Integer preorder will accept the preorder array, integer in order will accept the in order array, and then we'll be accepting all those integer pre-start, integer in start, and integer in end. Okay, so now we have taken all the arguments. Now here we'll be handling the base case. Here also we'll be handling the base case, and the first base case is the two cases that I'm going to discuss in the right now. Okay, so now notice This is the array right now we are giving in the question. That is the array. Let me observe the question once again. So yeah, that is -1. As you can see in the question, there is once pre-order in order. This is -1. That means here there can be a lot of questions and lot of example by what our program gonna run. So we might get example, matlab we might get example like this. This is having a lots of elements on lots of nodes. So we might get a case like this also when there is only one element. Let's say this is 5. So if there is only a tree like this 5, then what it will happen, do you know that the starting of in start and in end both will be same. Both will be same. That means in start, that means here the value of in start equals to in end, and if in start and in end the value is both 1, that means that is the starting and ending, that means there is only one element, so we cannot construct subtree. So here we cannot construct subtree, cannot construct subtree. So if that is the case, we cannot construct subtree. Sometime it might be that, let's tell this pre-start. So we call this pre-start in our program. This is pre-start because this is the starting point of this pre-start. And if we just get such a point that it actually ends. Okay, and this is the pre-start from where the program starts, and this is the preorder.length. So if we get such a scenario that this pre-start comes here where there is already not element, so this is also a stopping case where we have to stop our condition. That means we have to return our program. So these are the cases where we have to return the program. Okay, so this is one more stopping case, so we have to deal those cases also in our program at the first part, that if we get such scenarios, because now we are dealing with the array like this 3 9 20 15 7, so we are dealing. So we are actually right now dealing with those elements, and now let's write the program and we'll be understanding in more clear way. Okay, so we are back in the program. So now we'll be checking the base case. If the pre-start, that means the first element of pre-order exceeds the entire length, that is greater than equals to pre-order dot length. If this pre-start is greater than equals to pre-order dot length, or the in start is greater than in end not equals, because is greater than in end, because if there is in end that might also be a condition, so is greater than in end, so we'll be simply returning return null. That means this is the scenario when we cannot construct a subtree. This is the scenario when there's actually not any elements to construct subtree. So here we are handling no elements to construct subtree. Okay, now we'll be handling the second case. Now we have to construct the root. The root is the main of the tree, and we are constructing binary tree, so we must have a root. So now we'll be constructing the root. So we'll be calling tree node root, that is equals to new tree node. We always construct tree node like this, new tree node, and we'll be constructing with respect to pre-order of. We all know that the first index of pre-order is always the root, pre-order pre-start. So now we constructed the root. That means, let's understand this line. That means, notice this is the pre-order, and we all know in pre-order that the first one is always root, then left, then right. So we got to know that this 3 is the root, that 3 is the root. So with respect to that root, we just created the tree node root. So we just created this line that with respect to, we pass the value of this one, because this is the pre-start, that is the pre-start. This is called the pre-start. pre-start, and this entire length starting from here to here, this is pre-order dot length. Got it? And this is the in start. This is called the in start, and this position. Now what is our core focus is, now our main goal is to segregate it like this. We know this one is 9, this is 9, this is 3, this is 15, this is 20, this is 7. And now our main goal is to find the left tree and the right tree. That is our main goal. And we know this is 3 is the root. That means here 3. This 3 is the point that we know that this 3 is the root. But we don't know where is this 3. We don't know the index. So now our goal is to find the index. That means now we'll be finding the index like this: 0, 1, 2, 3, 4. So we'll be taking this element from here, this 3, and we'll be matching with all those. We'll be matching one by one with the loop. And once we match that 3, we'll be storing this index 1 in our in index. That means the value of in index will be, that is equals to 1. Why? Because we will be storing the index of it. So it will be an index of 1. Now notice one important thing from here. Once we get the in index, we get to know that this traversal order is left, then root, then right. That means we got the root. Now 3 is the root that exists here. We got it. So now just try to understand what we got. We got from here, that is all the elements in its left side, that is left, and all the elements in its right, these are right tree. So that means now we can conclude that 9, which is starting from 0 and before this index 1, this comes in the left part, and this all comes in the right part. These are all part of the right tree. That means that it starts with in index plus 1 value. So now we will be utilizing this in the code. So let's see. So integer in index, so we will be initializing this integer in index, that is equals to 0. So we just utilized the integer in index. Now we'll be checking for integer I, that is equals to in start. You might be thinking why this is in start. Notice we could also write that index 0 as I saw you in the diagram. But this program will recursively work. This is 0. Now few time later it will be 5, then 10, then 15, then 18, because this is recursion. So that value will get updated. That's why in start. So this is I equals to in start, then it will be running up to the value of I less than equals to in end, and then we'll be increasing I plus plus. Okay, now we'll be checking if in order of I, that means the elements of I, that is equals to preorder of pre-start. That means first element of the preorder, and once they matches, we will just update the in index by that index I. So it updated, and now we'll just break the loop break. So it got broken. Now we exist of the loop. Now our main motto that we have done everything, and it will automatically construct the tree. So what we have done right now, just notice Alt2. Okay, and now we are here. So now we have got the 3, we got the location of 3, we got the 3. So now we have already created a node like this 3 root node, because we have assigned value to root node. So we have got, now what we have to do, we have to create this left side. That means we need to assign value in our root dot left. Once we assign a tree value something like this, it will automatically assign a node like this. And notice we have already created the root node here. That means if we just copy and paste, that means if we just make somehow work the same things, somehow all the same things or same lines of code for this root, then here also node will be created. Now notice one more thing. If now if we just create one more node to its right, that means if we create an element to root dot right, and a same element like this to this, so it will automatically get an element and it will start constructing binary tree. And if the program again runs for this side, left side, and again for right side, again it works for cases left side and again right side. So we'll automatically get the value and our binary tree will get constructed. That means for that we have to assign value in root.left and root.right. In these two sections we have to assign the value, and then this, and how we can assign it, we have to create a same node like this where value will be assigned. Now the simple answer is recursion. If we just apply recursion, it will automatically create a node like here again until the terminating condition. So we will just now apply the recursion. So let's apply the recursion. Okay, now so we'll be assigning value towards the left. So now I have gotten, now we'll be assigning value towards the left. So root dot left. Now we'll be assigning, now will be this utilizing the same function build tree node. The same function but with some updated value. So integer root dot left, this is equals to this one. Root dot right. Root dot right, that is equals to same function. But now as we are constructing different trees, so we have to update the values. So now integer preorder, the order will be same, but and tree start. Now notice one thing, that we have to update the starting indexes. Now we had pre-start first one, but if you notice one thing, okay, notice here there was 3, and now this is left, this is the left side. Notice the 9, this is the left side, this is the left side 9. But what it becomes in the second step, when this 3 9 comes here, this also becomes a root. That means the value after this root plus 1, this root, and if you just observe one index plus one index, so we get the left, and this left becomes the root. It becomes the root for the next step. So we will be just passing this one, this left one, as the root for the second step. Did you notice? So now we'll be updating the value of left side. So this one will be period start plus 1. We updated the starting index. Now this is our main root of, this is our main root of left side of left tree in the pre-order traversal. Now we have to also update the in order. So it is in start, and we have already gotten the end side. So what is the end side? This is just in index minus 1. Let's again move to the tree. So our tree was this 9 3, that was our tree in order. So we got this. Let's again understand from here. Okay, copy. Okay, again we'll be understanding those things here, that what we are trying to do here. Now notice one thing, that we had 9 3 15 27. What this 9 3 15 27. So we got the in index here. This was our in index, that was our in index. Now we will be passing, now we'll be passing the end index. So what is the end index? Here this is the end index. That means if there was some value, that would be the end index. But that's not as, suppose guess there is a end index x, so x would be the end value. That means this end value would be in index minus 1, in index minus 1. So we'll be passing this in index minus 1. So let's pass in index minus 1. So this is integer in end. So instead of in end, we'll be passing in index, because now our end is updated. Now our end is in index minus 1. Or we could manually write here also that our in index becomes in index. So this is short form. Now this is, now we came to the right side, and now we'll be updating the root header bar. So this array will remain the same. And now the pre-start portion. So pre-start will get drastically updated. Pre-start will be plus 1 plus in index minus in star. So let's construct a tree. Okay, so we are here right now, and now we'll be constructing a tree to understand that one. So we require a tree to understand it better. So let's tell we have a tree where there is 10 as the root, and there is 6 15, and there is 4 8 4 8, then 12 18, and then 3 5, and we have 14. So now our core focus is that we'll be creating the pre-inverter traversal, because now right now we are observing. Okay, so we are right now observing here. So now we are noticing this one pre-start, that why this is, we are passing this one as the new value, that integer pre-start plus 1. So we are passing this one, that integer pre-start, integer pre-start plus 1 plus in index minus in start, in index minus in start. We're passing this value. So now we'll be analyzing this one. So let's notice one thing here, that pre-start plus 1. Why this is pre-start plus 1? So did you notice one thing? This was in order. So now again we'll be bringing our pre-order tree. So the pre-order tree was this one pre-order. This is 3 9 20 15 7. So this was pre-order. Okay, now we'll be constructing the pre-order traversal of this tree, the pre-order traversal of that tree, pre-order traversal. So let's construct the pre-order traversal. What will be the pre-order traversal of this tree? So this tree pre-order traversal, that means what? First there will be root, then there will be left, then there will be right. Root will be that first. So first we keep this root, that is 10. Then after root we'll be visiting left, so 6. Once we visit the left 6, once we visit this left 6, now it becomes the root with respect to this tree, then it becomes the root. So we again got a new root. So root again, it will follow the same system, left. So this is left, so we follow 4. Now we construct 4. After 4, this 4 again becomes the root with respect to new smaller tree. Again we visit, after root we visit the left, so left 3. Once we visited the left 3, we now visit the right, so 5. We visited the right 5. After this right we visit this right, 8. After this right we visit this right, so we actually provide 15. After that 15, now this 15 becomes the root. So as this 15 becomes the root, again we'll be visiting what? Left side. So we visit this left side, 12. So we visit the left 12. So again this 12, this 12 becomes the new root. So again what we'll be visiting? We'll be visiting the left side. Left is null, so we'll be not writing this one, or we can write it if required. So left is actually null. After left we again visit what? Right. So we keep 14. After 14, this is where we visited the right side. So now again we'll be visiting the right side, we'll be visiting 18. And if you notice, we have visited the entire tree. So now let's see, where is our root, where is our main root. This 10 is the main root. So where is the main root? Now if you find this root is in the first position. This is in the first position. So at the first position, or in start position, this is in start position. In start, not this is pre-start. So at the pre-start position there is the root. And if we find the root of the left side, or the root of the left tree, so 6, you can find this is the root of the left tree. That means this is just only pre-start plus 1. So we passed just pre-start plus 1 for this one. Notice here, we have passed here just integer pre-start plus 1 as the starting index. Notice here, this is pre-start plus 1. This is because of the starting index in left tree, but in the right tree again we have to pass the starting index. So now we have to figure out the starting index. So what if it becomes this or not? Now we'll be observing that one. So let's again look at the starting index. Okay. So for left tree we have passed the starting index, and for right tree we have to pass the starting index. So we can see here easily, clearly, that this is the root node of the right tree. 15 is the root node of the right tree. So now if you find the 15, there is the 15. this is the 15. That means we have to figure out this element. How we can figure out, that is the core focus, that we have to find out this 15. So if we just make a pre-order in order of this 15 like this, there is also the pre-order in order. So if we would find, so the general formula that would give us the result will be pre-start plus 1, pre-start plus 1, the index from here, plus in index minus in start. That means, again, for that, to understand this section we have to make a in order root of the tree. In order, we have to make an order tree. So actually what this section does, in index minus in start, actually it subtracts, it actually denotes the length of the left tree. So if we just subtract the length of the left tree, so what it becomes, the length of the left tree, that is 1 2 3 4 5. So from here, this is the root and the 5. So if we just emit 5 elements from here, we get this element. So we actually do this one to get this index, the index of this one, 0 1 2 3 4 5 6. So to get this index, we actually perform this logic. So I hope you understood this logic. So let's move to the question. So okay, and now this is integer in index plus 1, the starting of a right index. I could show you. Let's again see this also. Okay, so in start, so this was the in start, this was the position of in start, and this is in start plus 1. This position is the in start plus 1. So this is in start plus 1. So from here we have started our program, that means the right section, and this is the in end position, so that is in end. Okay, so this is in index plus 1 and it is expanded up to the in end. So we have constructed, so return build tree helper. So we have to return root from here. Once this entire tree is constructed, we have to return the root from here, then only it will happen, it will construct the tree. So we'll be returning the root from here, return root. Now again we'll be running the program. Is end line number 24. Okay, we have provided 2 semicolons. Again we'll be running the code. Okay, it got accepted. So let's again submit it. Okay, it got submitted and bit 40.89% of people. So we could also optimize this one using hash functions or hash map, like that type of thing. So we'll be optimizing in next session. So meeting in next session.